Hey guys, welcome back to another lecture video for Chem 115. In this lecture video, we are going to discuss simultaneous equilibria or competing equilibria. So I thought it would be appropriate for me to draw this cartoon of these two moles trying to go through this revolving door. That's typically seen in like fancy hotels or upscale casinos and all of that stuff. And so the idea is that when one of these cartoon characters enters this revolving door, and if they either go clockwise or counterclockwise, how will that affect how the other cartoon character will move with respect to this revolving door? And so hopefully as I go through this idea of simultaneous equilibria, this analogy of revolving doors will make better sense. So let's go ahead and start. And so simultaneous equilibria or competing equilibria is when two or more reactions are simultaneously occurring such that the product of one reaction becomes the reactant for the other reaction. This can also work in reverse. So for example, the reactant of the second reaction can act as the product of the first reaction to form the reactant of the first reaction. And so it's kind of hard to describe it without seeing it on paper, so we're just going to go ahead and do just that. And so this example that I've pre-written is magnesium hydroxide. And magnesium hydroxide is a typical substance that's observed in soap scum if your municipal water supply does not treat its water. And so the idea that if your municipal water supply does not treat your water, you typically have an accumulation of calcium and magnesium ions, such that when you wash dishes, you get like mineral deposits on it, or after you take a shower, or repeated showers, like over time, you get this buildup, this ring buildup, either in your toilet or shower faucet, etc., etc. And so this buildup of mineral deposits is composed of many different things, but typically it's like a hydroxide of magnesium or a carbonate of calcium, so calcium carbonate, magnesium hydroxide, and all of that stuff. And so if you guys have ever tried trying to clean that mineral deposit either on the toilet or your utensils or the outside of the faucet, it's pretty difficult. However, one of the cool things is that if you were to, for example, add vinegar, and vinegar is acetic acid. And so if you guys were to add some type of acid to this mineral deposit, you will see that it becomes easier to clean. In other words, some property of the acid will allow this highly insoluble substance to dissolve more readily. And so how does this work? Okay. So we're going to go ahead and look at the simultaneous equilibria that will explain why certain cleaners, or simply adding vinegar or acetic acid or some type of acid to this mineral deposit increases its solubility, thereby making it easier to clean. And so if we're looking at magnesium hydroxide, which is a slightly soluble, mostly insoluble substance, a small portion of it will produce its ions in solution, producing magnesium and 2 moles of hydroxide. And they're both aqueous. Okay. notice that one of the products is a hydroxide, and this is something that we've worked a lot with in the previous chapter. So hydroxide, with respect to acids and bases, is considered a base. And so when you add like a weak acid or a strong acid to this substance, so to speak, the hydrogen ion is going to react with that hydroxide. And so we have this hydrogen ion, and it can come from any acid source, and it's going to react with this hydroxide ion, which is a product of the first reaction. And so the resulting substance that's formed between an acid and a base is simply going to be water. And we're not looking at all the spectator ions, we're kind of taking all of that stuff away. And so here we have two reactions that's occurring. We have a reaction where magnesium, if we're looking at it just in the forward direction, the reverse direction does occur, but for now, for this demonstration, we're just going to think about it in the forward direction. And so we have this substance, magnesium hydroxide, and in the forward direction, we'll produce X amount of magnesium and X amount of hydroxide. And so when you add that acid to the mineral deposit, to the system, another reaction is occurring simultaneously, such that the product of the first reaction becomes the reactant for the second. And so as you keep on adding more acid, it's going to keep on consuming this hydroxide. And when you consume a product, what does Lacheys Principle tell us? It tells us that to replace the substance that was lost, it's going to shift the equilibrium in that direction. And so what we get is a net shift in our equilibrium such that the production of the ions is favored. And if the production of the ions is favored, then this magnesium hydroxide becomes more soluble, right? And so this is the reason why when you guys are cleaning your restrooms, trying to scrub all of that hard water out, soap will not do it. You guys need an acid. That acid is going to dissolve or absorb that hydroxide, producing water. And according to Lacheys Principle, it will inadvertently force this slightly soluble, mostly insoluble substance to become more soluble. Therefore, after some moment in time, with some elbow grease and lots of reagents probably, you guys are able to quote unquote get rid of the mineral deposits or the ring formed around your bathtub, toilet, utensil, whatever. Okay. And so the idea of simultaneous equilibria or competing equilibria is nothing new with respect to what we've done in the past. We're just adding a terminology to it. And so Lacheys Principle, that was a huge example of a simultaneous equilibria. It just wasn't stated or phrased that way, but it truly is. And you guys have seen simultaneous equilibria in past lecture videos for this chapter as well. And so the idea is that we have these two reactions that's going on. And now that we understand, so I'm going to go ahead and probably just rewrite this or just copy and paste this to Oh, what happened? Oh, I want to duplicate. I'm just going to go ahead and erase some of this stuff that I wrote down because we're going to go ahead and take this idea of simultaneous equilibria and take it one step further. Remember that this equation, this magnesium, the decomposition of magnesium hydroxide into its ions is going to represent one chemical reaction that's occurring. And so the second reaction, this hydrogen ion reacting with the product of the first reaction, which is the hydroxide, to produce water, is another reaction that's simultaneously occurring. If you guys recall from our equilibrium chapter, each of these chemical reactions have an associated equilibrium constant to it, such that the sum, actually, I should just write this down. The sum of both of these chemical equations produces H plus, and actually before I write the answer, remember that in the first semester of general chemistry, and we kind of saw it also in the equilibrium chapter this semester, when you're adding these chemical equations, you're crossing out what's in common on either side of the arrow. And so in this case, hydroxide is a common substance. And I think I need to balance my chemical equation first. Okay. So oh no, I'm fine. And so here, pink. When we're combining both of these chemical equations, only one of those hydroxides will be canceled, right, leaving one out. And so the resulting equilibrium that we get is H plus aqueous plus magnesium hydroxide solid produces magnesium ion one more mole of hydroxide, that's aqueous, and water. Okay. And so the sum of these two chemical reactions produces this overall chemical reaction. And if we're trying to incorporate the equilibrium constants to this, when you're adding these chemical equations together, the overall equilibrium constant will be multiplied with respect to each other. And so the first question that I'm going to ask you is, what would be the equilibrium constant that would represent equation number 1? Okay. And so equation number 1 is represented by KSP. Here we have the solid decomposing into its ions. Okay. And so we're going to say that KSP, the value of KSP of magnesium hydroxide, this slightly soluble, mostly insoluble substance, is going to dictate the equilibrium constant for the first reaction. Now, if you guys are looking at the second reaction, what would the equilibrium constant be to represent the second chemical equation? And so this one would represent Kw, right? So we have hydroxide plus a hydrogen ion plus hydroxide to produce water. And so if you guys were to multiply both of these together, you would get the overall equilibrium constant. Okay. And once again, this idea of multiplying equilibrium constants is nothing new to us for a second semester of general chemistry, because we covered this. We covered manipulating equilibrium constants in a couple of chapters ago. Okay. All right. And so this is just one example of competing equilibria. And there is another, I am going to layer this thing that we're doing with a specific problem, but I just want us to get into the hang of kind of understanding if your slightly soluble substance will be more soluble or less soluble based on the second reaction that's occurring. And I also want to explore more about, I also want to explore how your overall chemical reaction and your overall K will be expressed by the product of those two equilibrium constants. Okay. And so to tie up this example right here, since hydroxide is produced adding the acid will decrease the concentration of the hydroxide that was produced. Therefore, to replace what was lost, which is the hydroxide, the equilibrium in the first reaction will shift to the right, making magnesium hydroxide more soluble. Okay. And so what would make this reaction more insoluble? And so here if we have magnesium hydroxide, and once again it's producing magnesium ion and 2 moles of hydroxide. And this is just simply an exercise of Lacheys principle. What would we have to add to this chemical reaction to make magnesium hydroxide more insoluble? And so there's a couple answers to this. One, we can increase the concentration of our OH. And so if we increase the concentration of our OH by making the solution more basic, it's going to shift the equilibrium to the left if we increase the concentration of the hydroxide. Now, if you had said, if we increase the concentration of magnesium by adding, for instance, magnesium chloride or something like that, then that's also a possible answer. And so if you guys, let's think about this in terms of like your bathtub, right? So when you take a shower, let's just say like your bathtub, your shower is like super clean. There's no scum, there's no hard water buildup. As you guys take a shower, or if you guys take a shower the first time around, maybe you have some mineral deposit, but you won't see it yet because it's so small. But as you continuously take showers, as you continuously open and close the faucet, you're increasing the amount of magnesium that the ring of the faucet is being exposed to. And so over time, what you're doing is you're shifting the equilibrium to the left, making more, for example, of magnesium hydroxide that is found on the ring of your faucet, like the opening of your faucet. And so it's this continuous addition of magnesium that will increase the buildup of your minerals until it gets to the point where it's noticeable. It gets to the point where it's visibly noticeable, and then you're like, "Oh man, I guess I got to clean my restroom now." And so, that's one way that would increase the production of magnesium hydroxide, and it's also going to make magnesium hydroxide more insoluble. And so it's probably one of the reasons why it's not good for you to add a base if the composition, and I'm saying this with a big if the composition of your mineral buildup is magnesium hydroxide. And so typically the composition of your mineral buildup, it's not only magnesium hydroxide, it's calcium carbonate and some other things as well. And so if you guys are out in Target or Walmart buying some cleaning supplies, if you look at the back of that label, there's a whole bunch of chemicals. And each and every single one of those chemicals act to, to dissolve your slightly soluble, mostly insoluble compound, your hard water buildup. All right, so now that we've talked about cleaning up a restroom, let's go ahead and look at other reactions. Oops. So what if I have PbF2? So PbF2 is going to be our slightly soluble. So lead 2 fluoride is going to be our slightly soluble, mostly insoluble substance. And at this point, I'm not like alluding to any. I'm not alluding this example to the hard water, the restroom, the cleanup, and all that stuff. This is just purely theoretical at this point. So here you have lead 2 fluoride, and we know that a small fraction of lead 2 fluoride, even though it's mostly insoluble, will dissolve or decompose to produce lead 2 ion and fluoride ion. And we'll produce 2 moles of it. And so this equilibria is going to be described by KSP. Now, if you guys think about the composition or the nature of fluoride, so fluoride is the conjugate of a weak base. And so if you produce the conjugate of a weak base, then you actually will get a second equilibria or second chemical reaction that's going to occur. Remember that the conjugate of a weak base can react with water to produce OH minus and the conjugate acid. which is a weak acid. And so what is this simultaneous equilibria telling us? This is telling us that if you have lead to fluoride and you put it in water, a small fraction of that slightly soluble, mostly insoluble substance is going to release 2 moles of fluoride ions. And when it releases 2 moles of fluoride ions, that fluoride ion is going to interact with water such that a hydroxide ion and the conjugate, the weak acid, will be produced. And so if you were to take the pH of a solution that's filled with lead 2 fluoride, and you have to let it build up over time. It's not like, oh, just drop the water and it's good to go. So basically, if you take the pH of the solution should be more basic. Okay. All right. And so if you wanted to, if you wanted to write the sum of both of these chemical reactions, and this is something that I did not do in the previous example. Maybe I'll redo the previous example in just a second. I just wanted to get the main point across, the idea of the equilibrium constants and the overall K. And so if you are looking at the second reaction, the equilibrium constant that's going to describe the forward direction is going to be Kb. And so the K overall, I'll probably write it here, is going to be the product of Ksp times this by Kb, just in general. And so if you guys are trying to add both of these chemical equations, I want you guys to notice that the fluorides, although present in both on either side of these arrows, which allows them to cancel out, one of them has 2 fluorides, while the other one has only 1 fluoride. And so if you wanted all of the fluorides to be canceled out, what you will have to do is multiply the whole entire chemical equation by 2. Okay. And then you're going to go ahead and distribute that 2 to each term within this chemical formula. I'll go ahead and erase this. And so it looks like what we're going to get is 2 fluorides plus 2 water molecules to produce 2 hydroxides and 2 hydrofluoric acids. And so even though this equilibria is described by Kb, what do we do when we multiply each term in that chemical equation by 2? What do we do to the equilibrium constant, if you guys remember from chapter 14? Okay. And so for multiplying by a coefficient, we have to square that value. Okay. And so I'm going to go ahead and merely just bring this down. Okay. And so this is still equation 2, so I just kind of reversed it. It doesn't matter. And so here in this case, notice that we have equal number of fluorides now. And when we have equal number of fluorides, that'll allow us to cancel those out and add everything such that we get PbF2 solid plus 2 moles of water to produce 2 hydroxides and 2 HF and 1 mole of Pb2 plus. Okay. And so this is our overall chemical equation. When we combine both of these equilibria together. And so how would we describe the overall equilibrium constant Well, if you recall, the first equation is represented by KSP, and we really didn't do anything to the first equation, so there's no reason for us to change its actual value. And if you guys recall, the second equation is represented by KB. However, since we multiplied the original equation by 2, we have to square the equilibrium constant. So we're going to take KB and then we're going to square it. And then after that, we're going to multiply it by KSP to determine the overall value. Does that make sense? Okay. So let me go ahead and clean up my work here. For this example, I merely just wanted to drive this point home on how to get the overall K. But now that we've kind of understand that, or we remember that general process, let's go ahead and be a little bit more precise. And so here we notice that we have 1 hydroxide, and here we have 2 hydroxides. The hydroxides will cancel out because that's the only thing that's in common between both of these reactions. And so to cancel out that hydroxide, we would need to take this equation and we would need to multiply everything inside by 2, such that we would get 2 hydrogens, 2 hydrogen ions, and I'll probably do this in pink. So 2 hydrogen ions, 2 hydroxides, 2 water molecules. And that will allow us to cancel the 2 hydroxides. And so taking into consideration that fact, then we need to change our stoichiometry for the hydrogen ions, and we need to change the stoichiometry for the water molecule. And the only thing that we have left over on the product side is just magnesium and water. So we're going to go ahead and take away this term, and I'm just going to scoot this guy over. So this would represent the overall chemical reaction between these 2 simultaneous equilibria, these 2 simultaneous reaction. And since we multiplied by 2 in the second equation, we need to go ahead and take this Kw and square it. And so Kw squared times that by KSP will give us the overall equilibrium constant for the sum of both of these chemical equations. Okay? And so hopefully that kind of reviews this idea of simultaneous equilibria that we've looked at once before when we were going over manipulating equilibrium constants in chapter 14 of the Jesperson textbook. Okay. All right. And so what we're going to do is we're going to build upon this knowledge, and we're going to look at a couple of examples. We're going to look at how we can use the techniques learned here, the ability to manipulate chemical equations and determine their their new equilibrium constant, and we're going to apply that to determining the molar solubility of our slightly soluble, mostly insoluble substance. Okay. So let's go ahead and look at this problem. So we have silver, and silver can react with ammonia to form a metal complex, which is called diamine silver 1 ion. We want to calculate the molar solubility of silver chloride in water. And then once we calculate the molar solubility of silver chloride in water, we're going to compare this molar solubility to the molar solubility of silver chloride. This is what happens when you type things out. When, not Wayne, when okay. So this is what happens when you use Siri to write the problem for you. So we're going to compare this molar solubility to the molar solubility of silver chloride when 0.250 molar of ammonia is introduced to the system. Okay. So we haven't talked about metal complexes. That's a different chapter altogether. And so I'm just going to go ahead and give you guys the two equations. So we have this metal complex, diamine silver 1 ion, and it is representative. This is the chemical formula for diamine silver, right? So di means two, so there's two amines. Ammonia is amine in the nomenclature of metal complexes, and silver is obviously silver. So we have this silver chloride, and we want to first calculate the molar solubility of it in water. So this is something that we're familiar with. So let's just go ahead and do that first before we tackle the second part. So if we have silver chloride, or what is this? It is silver chloride, right? So we have silver chloride in water. And we know that when we have this in water, we're going to produce its ions, Ag+, Cl-, aqueous. And we can go ahead and represent this equilibria using the ice table. So we're not given any initial amounts in our problem. We're simply stating we simply want to determine the molar solubility of this substance in water. And remember that molar solubility is represented by the letter S, which is found in the change of our ice table. So we know that we have some amount of silver chloride that's going to be soluble. That's why it's minus S. And then we're going to put plus 1S and then plus 1S. It's a 1-to-1 ratio. And so at equilibrium, the equilibrium concentration of silver is equal to the molar solubility of silver chloride, which is just 1S. And the same thing goes for chloride. The equilibrium concentration of chloride is the same as the molar solubility of silver chloride. And to write the mass action expression, we're just going to write KSP is equal to the concentration of silver raised to the first times this by chloride raised to the first, because it's a 1-to-1 ratio. And we're just going to plug everything in here. And so we get KSP is equal to S squared, where S represents the molar solubility. And so to solve for S, we're going to take the square root of KSP. And the KSP is given to us as 1.8 times 10 to the negative 10. So 1.8 times 10 to the negative 10 is going to go inside the square root. And if you plug this into your calculator, and I'll go ahead and plug it into my calculator right now, we're going to report this answer in 2 sig figs. So we have 1.8 times 10 to the negative 10. Then we're going to take the square root of it. And what we get is 1.3 times 10 to the negative 5. And since this is referring to the molar solubility of silver chloride, we're going to say that it's going to be 1.3 times 10 to the negative 5 molar. Okay, so that's how much of it is soluble, or yeah, something like that. Anyways, and so the molar solubility of silver chloride is 1.3 times 10 to the negative 5 molar. And now we're going to compare the molar solubility to that when 0.25 molar of ammonia is introduced to the system. Okay. So let's think about the concept first so that we have an understanding of what our value should be. Okay. Let's go over this concept. When you add 0.250 molar of ammonia, if you look at these two reactions, this is telling you that silver is a product of the first reaction, but ammonia will react with silver, so it's consuming silver. So this is consumed to produce this metal complex. Okay. And so here in this case, since we are consuming silver, how will that affect the molar solubility of silver chloride? And this can be explained once again by using Lacheys Principle. So the disturbance in this case is the consumption of the product. To replace the product that was lost or that was consumed by another reaction, the equilibrium will shift to the right to replace the substance that was lost. In this case, it's going to try to produce more Ag to compensate for the Ag that was consumed by ammonia. And so overall, the equilibrium is going to shift to the right. And if the equilibrium shifts to the right, how will the molar solubility be affected for silver chloride? Okay. And so the molar solubility of silver chloride will increase. In other words, there will be more silver chloride that will be able to dissolve in the presence of ammonia. Okay. And so if since NH3 is consuming silver, which is a product in the first reaction, to compensate, or if you want, you can say replenish, the silver that was lost to ammonia, the equilibrium will shift to the right. making silver chloride more soluble. Okay. So that is the underlying concept that's happening in this simultaneous equilibria. And if the original molar solubility of silver chloride in water is 1.3 times 10 to negative 5. Okay. So here I'm going to put the molar solubility of silver chloride is 1.3, 1.3 times 10 to the negative 5 molar. Therefore, the molar solubility of silver chloride with NH3 should be larger than this value. And so this is in water. And so this is our control, so to speak. So the molar solubility is 1.3 times 10 to negative 5. So when we perform this actual calculation, which we will do in just a second, our answer should be much higher than 1.3 times 10 to negative 5. And so if your answer is lower than 1.3 times 10 to negative 5, then you did something wrong in your calculation. And so by understanding the principle, by understanding that chemical reaction and being able to predict what will happen, it kind of gives us this ability to check our work. Okay? So that's basically what I'm trying to convey in a very long-winded way. All right, so let's go ahead and perform this actual calculation. And for me to do so, I need to copy I'm going to copy this chemical reaction, and I'm going to, actually, you know what, let me copy this whole thing because I also need the KSP. And so I'm going to copy this and I am going to paste it just below this calculation. And I'm going to erase some stuff that I don't need. It's going to be a distraction. All right, so we have this simultaneous equilibria. For us to calculate the molar solubility of silver chloride in the presence of ammonia, we have to somehow combine both of these reactions together. And so when we combine both of these reactions together, we're going to cross out the substance that is present on either side of the arrow on both of these equations. And so silver is what's in common in both of these chemical equations. So when we add, or when we combine both of these chemical equations, we're going to simply cancel out silver. And so this is a little bit different than the other examples that I've shown you with magnesium hydroxide and lead 2 fluoride, where we had to like multiply the second equation by 2 just to make the ratios equal to each other. And so here we got kind of lucky, it's just 1 to 1. And so the resulting chemical equation that we get is silver chloride reacting with 2 moles of ammonia to produce chloride ion and silver, this is diamine, silver 1 ion. So this is a metal complex. And so real quick, metal complexes, so you have your transition metals, and these transition metals, they're attached to other substances. They're called ligands. And what's really cool about these metal complexes is that they are, they're the reasons why, our solution in lab is like super blue, or this bright, beautiful purple, or bright, beautiful red, and all of that stuff. So we won't have time to discuss it this semester, but feel free to look at, I can't remember the chapter in the Jesperson textbook, but it has to do something with the electrons overcoming this barrier and then falling back down to its ground state, and that electron is going to shoot out a specific wavelength of light, and that's going to produce the color that we see. Anyways, so we have this overall chemical reaction that's incorporating both the silver chloride and the ammonia. So remember, we want to assess how ammonia will affect the molar solubility of silver chloride. So having both of them in the same chemical equation is super important. It'll enable us to factor both of these scenarios in one go. Now, since you guys have combined the chemical equation, you guys have to combine your equilibrium constants as well. And so here in this case, the equilibrium constant is representative or is represented by the overall K value. And since you didn't really manipulate your chemical equations, you just added them, what you're going to do is you're going to simply multiply both of these values to get the K overall. And so the overall K is going to be 1.8 times 10 to the negative 10 times this by 1.8 times 10 to the positive 5. And the overall K value is going to be 3.24 times 10 to the negative 5. Okay. And so now that we correlated this chemical equation to its equilibrium constant, we can go ahead and we can go ahead and write an ice table to determine the molar solubility of silver chloride. And so the reason why I threw out the ice table, so if you guys look at this previous work that I've done, notice that to calculate the molar solubility, which is S, I need the mass action expression. And for me to determine the mass action expression, I need to know the components that's going inside this ice table. Okay. And so very similar to what I've done in the previous calculation, I'm just going to go ahead and write I, C, and E. And so we know, since we're trying to calculate for molar solubility, we want to know the value of what S is for silver chloride in the presence of 2 molar NH3. And so here in this case, if silver chloride is going to react with NH3, then we know that we're going to consume some amount of it. Hopefully that makes sense. And on the opposite side, we're going to go ahead and add those NH3s. Okay. I'm sorry, not NH3, but we're going to add the S, which is a reflection of the change. So here we have plus S plus S. And since this is a 1-to-1 ratio, we're just going to put in like 1S and 1S. And so before we add everything up, we need to see if we have any initial concentrations. And so we're going to go ahead and look at this problem one last time. We're going to compare the molar solubility to the molar solubility of silver chloride when 0.250 moles of ammonia is introduced to the system. So that last part in that last sentence implies that we do have an initial concentration of ammonia, and that's going to be 0.250. And so in this ice table, we're going to put in 0.250 molar concentration, and it didn't really tell us any initial concentrations for the other substances. And we're just basically working with what we have. And so here we have 0.250 minus 2s plus 1s plus 1s. So these are the equilibrium expressions for each of these substances, ammonia, chloride, and this metal complex, diamine silver 1 ion. That's great. Now that we have the equilibrium expressions, we can go ahead and write a mass action expression that's representative of this chemical equation. And we know how to do this from prior chapters. Now, you might ask yourself, well, there's a whole bunch of K's, which one do I use? You have to use the overall equilibrium constant. So this is the reason why I had to review that concept, just to kind of remind you how to incorporate what we've learned in the past to what we're applying in this lecture video. And so the K overall is 3.24 times 10 to the negative 5. And so we have K overall, which is going to be 3. I even forgot it. So 3.24. Okay. So 3.24 times 10 to the negative 5. And K is unitless. Now let's talk about the mass action expression for this. So remember, when we're writing the mass action expression, we're only writing it for substances that are either aqueous or gaseous in phase. Notice that this silver chloride is a solid, so we're not going to include that in our mass action expression. And so this is the reason why I didn't really write minus S here. I can write minus S just for completion, but I know I'm not going to include it in my mass action expression. All right, and so my mass action expression is going to be defined by the concentration of chlorine at equilibrium to raise to the first power times this by the concentration of my metal complex raised to the first power. And then this is going to be divided by the concentration of NH3 this ammonia that we added raised to the second power. And all we're going to do is just plug in this expression, the equilibrium expression, into where it's located in our mass action expression. And so here we have S times S over 0.250 minus 2S. And so that reduces to S squared over 0.250 minus 2S. And that's going to be 3.24 times 10 to the negative 5. So this shouldn't be something that's new to us. We did this a whole bunch of times in the previous chapter for acid-base equilibria. And so here we have a magnitude of times 10 to the negative 5. That's far, far less than 1. And so you guys can even check your work. So this whole term, we want to see if we can ignore this. And one way that we can ignore this is to determine whether or not the initial concentration is going to be far greater than our K overall times 100. And so the initial concentration is 0.250, and the K overall times 100, so that's 3.24 times 10 to the negative 5 times 100, and that's going to be 3.24 times 10 to the negative 3. Okay. And so if you guys want to compare those values, I'm simply going to move that decimal 1, 2, 3 places to the left, just to give it some perspective. And so if you look, 0.250 is far, far greater than 0.00324. So since that statement is true, then that means I can ignore the item that's in the denominator. Actually, real quick, I forgot one thing, the squared. Okay. Yeah, I have everything. Okay. All right, so basically our algebra just boils down to 3.24 times 10 to the negative 5 equals to s squared over 0.250 squared. And so this is clockwork at this point. We're just going to go ahead and take 0.25 and square that value. That's going to give us 6.25 times 10 to the negative 2. So I'm going to go ahead and multiply. I'm going to multiply that by 6.25 times 10 to the negative 2. So these two are going to be multiplied times this by 3.24 times 10 to the negative 5. And here I get 2.03, if I round to the correct number of sig figs, times 10 to the negative 6. And that's equal to s squared. So if I take the square root of my answer, I'm going to get a value that is 1.42 times 10 to the negative 3. Now remember what S represents. S represents the molar solubility of silver chloride. Now if you look at our answer, 1.42 times 10 to the negative 3, since it's a molar solubility, we have to include the molarity. So I'm going to copy this. Now if you guys look at our answer, and if you go all the way up to this statement here, right? So remember we qualitatively assessed what will happen to the molar solubility. So since ammonia is consuming silver, which is a product in the first chemical reaction, right, that you guys see here, to compensate for the silver that was lost to the ammonia to produce the metal complex, the equilibrium of the first equation will shift to the right, making silver chloride more soluble. And so here we can quantify this this concept. If we look at what its molar solubility is in water, which is 1.3 times 10 to the negative 5 molar, and we've just now calculated the molar solubility of silver chloride in the presence of ammonia, which is 1.42 times 10 to the negative 3. And so we predicted that this value, the molar solubility, should be larger than 1.3 times 10 to the negative 5, and it is. 1.42 times 10 to the negative 3 is much larger than 1.3 times 10 to the negative 5. So you can see that this silver chloride has become more soluble by almost 2 orders of magnitude, okay, just in the presence of ammonia. And so if you guys are thinking about this in the scope of like cleaning your bathtub, cleaning like the mineral deposits, the buildup, that ring around your faucet, toilet, whatever, it kind of gives some relevance as to what we're doing. Okay, we're allowing this silver chloride, which is mostly insoluble, slightly soluble, mostly insoluble. It's making it much more soluble in the presence of ammonia. Okay, and so the calculation to perform the calculations, the techniques that we used, was nothing new to us. This is everything that we've just kind of built up from chapter 14, when we were first talking about equilibrium. So Lacheys Principle, we talked about manipulating equilibrium constants by either squaring them, square rooting them if you're dividing your coefficients, or you're multiplying your coefficients. When you add your equations, you multiply your equilibrium constants to get the overall K. And then once we have this overall equation, we're simply using the ICE table, plugging in what our initial concentration is, depending on the problem, depending on what the problem gave us. And since we're trying to look for molar solubility, we're trying to determine S, right? Not X. S in this sense with respect to slightly soluble salts represents its molar solubility, how much of it is actually soluble, producing its ions. And then here we just built a mass action expression, and here once we have our mass action expression, we used this technique to ignore the change in the denominator. And so here in this case, once we obtain the molar solubility, and we're done, right? And then finally, we compared this molar solubility to that of the molar solubility in water, which is our control. And we were able to quantitatively determine that, yeah, in the presence of ammonia, silver chloride is much more soluble by 2 orders of magnitude.